Welcome to this video reviewing pointers in ARM assembly. First off, what is a pointer again? We typically see a diagram like this where you actually have a pointer pointing to a variable with a particular value of interest. The pointer has a value as well. In this case, the pointer's value is the address in memory of where that variable is located. Next thing to review for ARM assembly is the difference between data memory, the data section of memory, and your code or text memory, the code or text section of memory. This is the same whether you're using the TIVA-C microcontroller or the MSP432 microcontroller. Those are both ARM microcontrollers, so this type of code would run on either of those. In this case, we have our two sections, the data section, where one variable is initialized, my var, initialized with the value of 0. And we have the text section, which is where any constants are located, as well as your code, like the main program down below. We have two constants, my const, which is initialized to a value of hexadecimal, all Fs, basically -1 for 2's complement number, and my pointer, which is a constant. It has a value of my var. That's the memory location where the my var variable is located in the data memory. So to look at these two sections in more detail, the data section, again, that's where my var was initialized. You can read and write to the data memory. You can modify values in there if you wish, and you can, of course, read those values. But unfortunately, you can't directly access this memory from your main program. Your main program is in the text section of memory, and you're not able to use addresses directly in the data section because that's a different section. So if you want to access a variable in the data section, you have to use a pointer like we've initialized in the above code. The next section, the code or text section, that is, again, where your code is located, but it's also where any constants you want to define are located. We have those two constants, my const and my pointer, initialized there. You can directly access this memory within your main program. You see that in the main where we load in the addresses for my pointer into R0, or the value for my pointer into R0 and the value for my const into R1. But the text section is read-only. You cannot change or write to this memory. It won't. It's just unable to be modified. Now, to look at this code in a little more detail, we'll look at pointers in ARM assembly here. So first of all, the size of a pointer for a 32-bit system, which is what our ARM core is for either the TIVA-C or MSP432 microcontrollers. It's a 32-bit size variable to hold an address. So pointers are always 32 bits. It doesn't matter what the pointer is pointing to. In the above example, a pointer is pointing to another 32-bit value, but if my pointer is pointing to a byte variable, or if it's pointing to an array or a structure, it would still be 32 bits to hold the address, because that's the address size for a 32-bit system. If you're working with a different system, like a 64-bit processor, then your pointers would be 64 bits instead. But for us, they're going to be 32 bits with our microcontrollers. Where do you actually declare a pointer? Well, that's up to you. You can either declare it in the data section or the code or text section. And they can point anywhere. They can point to variables or constants in the data or in your code or text sections. The example that we looked at, my pointer was declared in the code or text section, basically as a constant, and it was pointing to a variable in the data section. This is how we'll typically use pointers with our ARM assembly code. But if you want to actually modify the value of a pointer, basically change where that pointer is pointing to, that could be useful in like a linked list. Then that pointer would have to actually be defined in the data section so that you can actually write to that memory and change where the pointer is pointing to. But note, if you have a pointer in the data section, then to access that pointer, you need an additional pointer from the text section to the data section so you can access it and modify it with your main code. Last thing is just to look at a couple of examples. So our first example is that code we looked at. Is an example of how to actually modify or use a pointer to modify a variable. So the main program above, we actually overwrite the value of the variable. We load in the value of my pointer, that's the address to my var. That gets loaded into R0. So R0 is a pointer. We load the constant value of my constant to R1, and then we use the store instruction to write that value, that -1 value, into the memory location pointed to by R0, which is the same as the value pointed to as from my pointer. So we'll overwrite the 0 of my var with a -1 or with all F's in hexadecimal. If you wanted to read that value of my var instead, then just use a load instruction. Down below, we have my pointer. We're going to load that value into R0, so R0 is a pointer now. And then we're just going to, again, use those square brackets to read from the address in R0, and that value, whatever value the pointer is pointing to, is going to be loaded into R1. Okay. Our next example is going to be a little more sophisticated. What if we use a pointer to access an array? And we'll also demonstrate the different addressing modes that we have. These are all indirect memory addressing modes because we're using an address from the pointer to access some part of the array. So we have the array and data memory. You can just list multiple values to form each value of the array. So this is just 5 values, 10 through 50. And then my pointer is pointing to the beginning of my array. So let's go assume that we've run an instruction LDR R0 my pointer, so the address that my pointer is pointing to is in R0. What if we run this first instruction LDR R1 and then in square brackets R0? Well, since my array is at the start of our data section in our data memory, and my pointer is pointing there, and R0 is a copy of the value of my pointer, my pointer in R0 will equal 20 million hex. That's the beginning of the data section in memory for our TIVA-C microcontroller or our MSP432 microcontroller. Since it's the beginning of the array, when we read from that with that LDR instruction, R1 will read the first word value, first 32-bit value from that array. That's the value 10. The next instruction is similar, LDR R1, and then in square brackets we have R0, comma 4. This is reading the word value that's going to be one word later. In square brackets, what happens is R0, you're adding 4 to that address, an offset of 4 bytes. So we'll read from 4 bytes later. The first element of the array is 10. 4 bytes or one word later is a second element, value of 20. 20 will be loaded into register R1. Note though, we do not change R0 with this instruction. This just modifies the address that you're actually going to read from or write to if this was an STR, a store instruction. This next instruction is very similar. It is LDR R1, and you have R0, comma 4 in square brackets with an exclamation mark after it. It's almost identical, but the exclamation point makes this a pre-increment instruction. You actually pre-increment R0, so it's like plus R0. So you add 4 to R0, and then you do the load instruction. So this would be, if R0 is initially 20 million hex, R0 would be changed to 20 million and 4 hex. And then you read the word value from that address, which is the same word value that we saw in the previous example, previous instruction. R1 will read that, or will get that 20 value from the array. It's the second element of the array. Let's say if instead we run this instruction, LDR R1, and in square brackets you have R0, then you have a comma, and then you have 4 outside of the square brackets. This version of the instruction looks a little strange, but it's It's similar to the last two instructions, but it's a post increment. It's basically doing R0 plus plus. So what happens is you will go ahead and do the load. You'll read the word value from the address or from the location R0 is pointing to. That's pointing to the beginning of the array. You're going to read the first element. That 10 will go into R1. And then afterwards, R0 is incremented by 4 bytes. So it's 20,000,004 hex at the end. So both of these, the pre-increment and the post-increment, could be useful if you want to modify this pointer in like a loop, if you keep on accessing different parts of an array. The next example is, what if we use an additional register? What if R2 equals 4 and we run this instruction, LDR R1 and then in square brackets R0, comma R2? That's functionally equivalent to what we've seen just a little earlier, where you have R0 and 4 in square brackets. It's just going to be the sum of the values of those two registers, R0 and R2. Add those together. That'll be your address you're going to read from. That means it'll be 4 bytes more than R0, one word later in the array. So you're not reading at the beginning of the array, you're reading the 4 bytes or one word later, which will be the second element of the array. So you'll go ahead and do the read. R1 will get a value of 20. And that's it. With this instruction, R0 and R2 are not changed at all. And then lastly, what if R2 equals 1 and we run this instruction instead, LDR R1 and then in square brackets R0, R2 and then LSL2. So this instruction is very similar to what we've seen again. What this will do is, for the address, calculate R0 plus R2 multiplied by 4. It'll actually be R2 logically shifted left by 2 bits. A shift left is equal to a multiplication, so by 2 bits it's multiplying it by 2 twice. So it's R2 times 4 plus R0. In this case, that's R0 plus 4 again. We'll read the element that's one word 4 bytes after the start of the array where R0 was originally, where R0 is pointing to. So that 20 value, the second element of the array, will be read into R1. And again, this instruction does not modify R0 or R2. However, this is a really useful instruction to use if you want to access an array using an index. R0 would be the pointer to the beginning of your array, and then R2 would be an index to which element of the array you want to read or write to, if it was a store. R2 is a 1, so you're reading the second element of the array in this case. Okay. Just a couple more examples before we finish up our review. Using a pointer to read a value which is not a word. So in this case, this is an array again, but it's just a byte array. Each value is 8 bits. So if R0 has the value of my pointer, how does this work? Well, if you do LDRB, R1, comma, and then R0 in square brackets, you just read, again, from the beginning of the array, because that's where my pointer is pointed to. My pointer and R0 are going to have that same value, 20 million hex, because the beginning of the array is at the beginning of the data section of memory. You read the first element of the array. That 1 is going to go into R1. You read that because it's just reading 1 byte with the LDRB instruction. You need to make sure whatever form of load or store you use matches the size of the data you want to read from a memory location. In this case, it's a byte, so we need to use the byte form of the LDR. What happens if we instead run LDR R1 and then square brackets R0? That's reading a word value from where R0 is pointing to. It's an actual address, so it reads a full word, 4 bytes from that memory location, the beginning of the array. R1 will have the value of hex 04, 03, 02, 01. Those are the first 4 byte values of the array that were stored in memory using little endian byte ordering. You might accidentally write this. This is a bug in your code if you're trying to read a byte value, but you used a word size load to do that. So if you do that, in this case, you read too many values. You read 4 values of the array and put it in the register R1. If you used a smaller version, if you were trying to read like a word value and you used LDRB to read a byte, you'd only read a portion of the value that you wanted and put that in the destination register. Both would not be correct. And then lastly, example 4 is how do we use a pointer to access an I/O register? We'll do this quite a lot. If we're working with I/O, you might define just what the I/O register name is and the address it's located at. There's 2 examples, one for the T/C microcontroller and then one for the MSP432 microcontroller. To access that, just in the text section, define the pointer, define the address where that I/O register is located, and then you can use a load or store to access it. Note that most, not every, but a lot of the I/O registers are 8 bits wide, so you would typically use LDRBs or STRBs to read or write to those I/O registers. There are some that are 32 bits wide, and for those you should use a regular LDR or STR. So one example is for the T/C microcontroller, the GPIO port F data register, so that's any input or output data to the port F. You define that address, you load it into R0, and then we do a LDRB where we read from that address and read a byte into R1. So that would be, maybe I have a switch off of port F and I read the byte value in, then I need to test to see if the switch was pressed or not pressed. For the MSP432 microcontroller, an example, P1in is just the input register for port 1. Again, we have some switches there, so maybe I want to read an input from that port. Get the pointer into R0 again, and then just use square brackets, read from memory location that R0 is pointing to, and put that byte value in R1. And then, of course, you need to do some testing to figure out if the switch you're interested in is pressed or not. I hope this review of pointers and ARM assembly helps. Thank you for watching.